Okay, yeah, welcome to my talk, Fuzzing and Testing Security of Kubernetes Admission Controllers. My name is Benjamin, and I will guide you through that wonderful presentation and the demos I prepared. But before we start, one question. Who here uses Kubernetes? Okay, and who here uses fuzzing? Okay, at least like one person, because in this talk we will combine two like complex techniques into into kind of a tool we built. But I will show you later. Okay, so first of all, a little bit about me. As I said, I'm Benjamin. I do cloud and Kubernetes security stuff and everything there. So I give trainings, I do consulting, I do security research. I'm also a CTF player at Fluxfingers. We are a German capture the flag team from the University of Bochum. I studied IT security there. I'm also the DEF CON Kubernetes CTF co-organizer. Who here is familiar with DEF CON? It's like a large security conference in Las Vegas every year. And there we have a, whoops. Yeah, image is gone. I don't know, is it? Oh, there it's back, okay. And I'm like a co-organizer for that security event at DEF CON. So yeah, be sure to check that out if you want to like Kubernetes security stuff and everything. And on Twitter, you can find me under my handle, Paketo or Packet0. Okay, let's head into the agenda for today. I will first of all do like a brief introduction to Kubernetes with the Kubernetes 101, that like everyone is on the same level. Then I will give an introduction to admission controllers. I think some of the folks here that are familiar with Kubernetes are also familiar with Kubernetes admission controllers, how they work, what they do, when do we use them, and I will give an example and also demo a standard admission controller we use in Kubernetes. And then I give you an introduction to fuzz testing or fuzzing, and we'll also explain a little bit what is fuzzing and give you an example of fuzzing. And in the end, we will combine the two previous points into how can we use the previous learned things and combine them together. Okay, let's head into the Kubernetes 101. So what you need to know about Kubernetes is you need to know it's open source. It's a container orchestrator. So basically, it's for managing microservices. So we need that in order to like manage our many containers we have nowadays, and that's why we have Kubernetes. There are also like various Kubernetes distros out there. So for example, Google in the Google Cloud has its own Kubernetes distro, GKE, the Google Kubernetes Engine. Then Azure, for example, has their own Kubernetes, which is called AKS, the Azure Kubernetes Service. AWS has its own Kubernetes, which is called, I don't know, it's like EKS should be, Elastic Kubernetes Service. And then we have, for example, other distros like Rancher Kubernetes, which is Kubernetes you can run on-premise, or we have OpenShift, the Kubernetes of Red Hat. We have Tanzu from VMware. So we basically have like a landscape that we also have for Linux distros, right? Because if we talk about Linux, then we don't have the one Linux system, it's always Debian or Red Hat or Ubuntu or something like that. And the same we have in Kubernetes. So normally, if we talk about Kubernetes, we need to define which Kubernetes we are talking about, because each Kubernetes is a little bit different to other Kuberneteses. And the last thing is Kubernetes is open and extensible. I put that in here because that's important for the talk. That means you have like a standard, let's say, definition of the Kubernetes API. So there is kind of like a Kubernetes standard that all of the various Kubernetes distros follow. For example, in every Kubernetes distribution, you can deploy a pod or a deployment or a service, right? That's something all of those have in common. And when I want to create, for example, a custom resource, like I will show you later, for example, I have prepared something called food delivery. Then there's a food delivery custom resource in the Kubernetes API. So I can deploy like food delivery objects into Kubernetes. And that's what we call a custom resource definition. So we can like extend the standard Kubernetes API with our own objects. And normally, if we extend the API with our own Kubernetes objects, for example, an operator or a controller, which are like kind of the same, they watch or they pick up those custom deployed objects by us and then create something, then they create something different inside of Kubernetes. So for example, there is an operator called the Elasticsearch operator. Some of you might know it. It's the Elastic Cloud on Kubernetes. And if I deploy that one, I can create Elasticsearch objects into Kubernetes. And then the operator picks up these objects and like kind of transforms those Elasticsearch objects into valid Kubernetes deployment and pods, and then creates like the Elasticsearch deployment and pod. And that's why we need the custom resource definition to make managing of like complex resources a little bit easier. Okay, then let's head into admission controllers. Some of you might know this picture. That's from the official Kubernetes documentation. It basically says that if on the left there's an API request coming in, so I do my kubectl get pods, for example, or something like that, or I create a deployment, then it's first the API HTTP handler like gets the request, then we're running through the authentication authorization chain. So basically we're checking, or Kubernetes checks, okay, who is the user that tries to create a deployment, and is he allowed or is she allowed to create the deployment, or is he or she allowed to do the action they want to do? And afterwards, we're running through the first admission phase, which is the mutating admission phase. So Kubernetes has a mutating admission controller that can mutate objects. You can think of it a little bit as when you try to deploy a Kubernetes manifest, for example, the deployment. I could write a mutating admission controller that mutates the name every time to something, for example, ABCD or something like that. So I can put in there my own custom name because I can mutate the manifest someone's trying to deploy. Then we are heading into the object schema validation. So after the object is mutated, it's checked, okay, is it still like valid JSON, valid YAML? And then we are heading to the validating admission phase. The validating admission phase is very, very interesting because what you can do with it from a security aspect is you can, for example, try to block incompliant resources. So for example, you can block privileged pods, for example, or privileged containers, or you can block containers that try to use host namespaces, something like that. So validating admission controllers are very nice to actually block incompliant resources from being deployed into the cluster. Oh yeah, something, I don't know why it's... Can you get back up? Yeah, okay, it's coming again, okay. And after we're running through the validating admission chain, after that, it's persisted in the etcd database. So it's not pushed into the database until we're running through all of that validation and mutation. And what's also important to notice here is that I cannot mutate an object after it has been validated. So if I mutate an object, if I mutate an Kubernetes object, it's every time it's validated afterwards. So there's normally not a way to bypass certain validation. Okay, the question here is, why do I need them? I explained it a little bit already. The first thing is, there are powerful tools to just enforce your policies, whatever policies they are. So for example, compliance policies or like naming conventions, naming policies, something like that. You can enforce everything with it. You get like the raw API, you get like the raw manifest that's deployed to Kubernetes, and you can check on every field that's set in the manifest and can validate every field on your own. So for example, we can write an admission controller that doesn't allow privileged containers in the cluster, or that doesn't allow a container to run as root user. We can also mutate a manifest to remove all capabilities from a manifest or something like that. So everything you can think of, you can do with those admission controllers. But the interesting part here is that we can also validate Kubernetes objects for custom resource definitions. So what I explained earlier, so think again of the, for example, Elasticsearch operator or the Elastic Cloud on Kubernetes. Somehow Elastic needs to verify if the object someone is trying to deploy are valid, right? If I write an Elasticsearch object, how do I know if it's valid, or how does the software not know it's valid, right? So they have like an admission controller that just checks, okay, is this a valid manifest? If it's a valid manifest, okay, go through. If not, okay, I'm gonna block it. And that's where we need admission controllers. So how does it gonna look? We have, for example, that's a standard admission configuration. We can specify, for example, the rules. So for example, this admission controller says on every pod create in a specific namespace, we send all of the manifest for the pod creation. We send that to the service here. That's in the namespace example namespace. The service name is this this example service. And then every time a pod is created, a HTTPS request is sent to that service inside of Kubernetes, and behind that service there needs to be a pod that does like the validation logic and everything. So that's like a basic example of an admission controller. Okay, and let's head into fuzz testing. And don't worry, I have like examples or practical demos for it like later when we are done with the theoretical part. So fuzz testing describes the automatic testing of software with random generated input data to find crashes. That's said in like one sentence. So basically what we do is we generate a bunch of random data, can be bullshit data, but it's random data, and we throw that against some input we have. For example, it could be binary. For example, it could be it could be some kind of embedded software, or it could be some kind of Ethereum contract or something like that. So we just generate random data and throw it against some input source we have. And we hope to generate an input that we hope to generate an input that our input software crashes. So if we find something like that, for example, we might have like a critical security bug, for example, buffer overflow or something like that. Okay, we have like different types of fuzzers. So for example, we have a generation-based or a mutation-based fuzzer. That kind of depends on whether the inputs are like generated from scratch or if we modify existing inputs. So for example, a generation-based fuzzer like generates this all from zero. So it starts from nothing and generates input sources. If we have a mutation-based fuzzer, we already have inputs and we only mutate those inputs. Then we have like a dump fuzzer, like an unstructured fuzzer, or a smart fuzzer, a structured fuzzer. Basically, an unstructured fuzzer generates really random data and doesn't know the structure of the input data. And the smart fuzzer knows the structure of input data and also knows, for example, which types it needs to generate. So if we have as input source a string, then it generates a string and not a number, right? That's like the easiest one to do. And then we have white, gray, or black box fuzzing. And that is something you might know from for example, from pen testing, which basically means, okay, how much information does the fuzzer has about the program? Black box would be, okay, I don't have any information. White box would be, I have the full source code and I know, and the fuzzer knows where to look, for example. What are like popular fuzzing projects? Some of you might have heard of, for example, Google OSS Fuzz, which is like the largest fuzzing project we currently have, running on like 100,000 VMs in Google Cloud, running by Google, by P0. It's a fuzzing project to fuzz open source projects. So if you have an open source project, you can go to Google and ask them, hey, Google, can you fuzz my open source project? And they will fuzz your project and try to find security critical bugs in it and report them then to you. And then we have, for example, Fuzzware, that is for fuzzing embedded systems. And we have something called RiverGuard that is built by Neodyme, the company we are like coming from. Is for fuzzing Solana transactions. So you see, a fuzzer can really, or fuzzing can help us to detect like security vulnerabilities in like really different types of projects. Okay, and let's look at kubefuzz, which basically combines the previous two mentioned technologies into like one, into one tool. So the idea is to fuzz Kubernetes admission controllers. And the main problem here is, or the main problem we recognized in admission controllers is, okay, how can I test my admission controller? And the second thing is, how can I test, for example, closed source admission controllers? So if you deploy any software into your Kubernetes, how can you verify that the software you're using is safe? Or how can you check whether the validation of the custom resources you're deploying is done correctly, right? Because it can be quite critical if the verification or the validation of the objects is done wrong. For example, if I manage to bypass an admission controller and that admission controller and the operator that like that works with the manifest deployed into Kubernetes tries to create, for example, a database based on the object I try to deploy, and the object is somehow falsely and cannot be and cannot be used by the operator, then the operator might be crashing. And then is the question, okay, if the operator crashes, what is the state of my database, right? If the operator manages databases, or if I have an operator that manages my Elastic cluster, if that operator crashes, okay, what is the state of my Elastic cluster then, right? So what happens to my Elastic cluster if I deploy a faulty manifest to that operator and manage to crash the operator somehow, if the input sanitization is done like falsely? Okay, so the idea here is to create random manifests, throw those against the Kubernetes API, parse the answer from the Kubernetes API, and adapt the corpus. So a corpus in fuzzing is something where kind of like the results of our fuzzing are saved in, and based on the corpus, we can then mutate or build like new inputs. Okay, what findings can we expect? For example, we can find crashes in Kubernetes admission controllers or operators. Whoops, that was too quick. We can find crashes in Kubernetes admission controllers or operators, which can result, for example, in bypasses in the admission chain. A really critical bypass example would be there's, for example, a kernel module operator in Kubernetes. If I deploy an object for that kernel module operator and the input sanitization is not done correctly, I maybe can deploy a kernel module into Kubernetes that's like, that's used by the operator, and the operator then tries to deploy some kernel module that's basically a bullshit kernel module. And that might lead into like crashing the Kubernetes node itself and leads to like an unstable Kubernetes cluster. Okay, what other problem can we expect? So if you remember the validating webhook configuration I showed you earlier, there's something else we need to have a look at, because there's a specific failure policy for each webhook. That failure policy is normally set to ignore, which basically means like a fail open. Companies do that because they don't want to like block deployments from being deployed by their admission controller if the admission controller fails. So if the default is, or the default is fail, that means that if you try to deploy a pod, but the admission controller is, for whatever reason, isn't reachable, then the manifest isn't deployed. And it's basically, it's not deployed, and you cannot deploy anything into the cluster until the admission controller is up again. So that's why companies like to set their failure policy in admission controllers to ignore. That means you can bypass every admission controller that you are able to crash. Okay, and let's head into some demos. I hope it was not too confusing. Oop, it's gone again, but we'll be back online. Oh, I think it's. Yeah. Okay. 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 So, well, okay. I have a standard Kubernetes cluster here, which is running some pods. Whoops. You can see that there's Kyverno installed. Some of you might know Kyverno. Kyverno is like a standard Kubernetes admission controller where we can write our own policies in order to block certain things. So for example, what I've created here, or what I want to show you is, I've created like a standard pod escape here, which basically like, gives me root on the Kubernetes node. This thing basically says, okay, I create a container with the name breakout, or a pod with the name breakout. It has a container with the name don't look at me. The pod has the host PIDs mounted inside each container, so I can see like every processes running on the host also inside of my container. I have set privilege to true, so it's a privileged container. And what I can do then is I can do namespace enter, so I enter the mount namespace of the process with the process ID #1, which is like the init process. And if you know, like the mount namespace of the init process is the root file system of a Linux system. So I start like a bash there. And if I do that, you can see that if I do, for example, that if I, for example, now list all of the containers that are running on the node, you can see that there are like many containers running, and those are all the containers that are run on my Kubernetes node, right? So what we can see, for example, if I do, let me do it a little bit larger. You can see that there's this breakout pod running for like 27 seconds, so that's the one I recently started, and yeah, you can also see that I'm now on the node. There's also, for example, the etc Kubernetes folder, which are all of the like standard configs we find on a standard Kubernetes node. Okay, and now I want to block that. So now I want to use my admission controller, in this case Kuverno, to block this from happening. What I can do here is deploy a policy, and that policy says disallow privileged containers. And what it does is it checks whether a container is privileged or not. So, for example, it checks here up for the spec containers.all. Yeah, for all of my containers, it checks if the security context.privileged, it must be false, right? So that's basically the rule it tries to validate. So if I deploy that policy and now execute the run again, you can see that I get like an error message from admission webhook validate Kuverno service. It says privileged containers mode is disallowed. The fields security context privilege must be set to false. So now what happened is I tried to deploy a pod. It got sent to an admission controller. The admission controller picked it up, tried or validated it, and said, okay, this is not a valid manifest. I don't want to have it in the cluster, and rejected it basically from being deployed. Okay, so that is how an admission controller works. And now I'm going to show you how we can translate that one into fuzzing those admission controllers. And I have a small example here. So there is a food delivery order, CRD, inside the cluster. I can also show you that one. It does look like this. This is basically like a custom resource definition inside of Kubernetes. And we have, for example, properties like a delivery address, a coupon code, yeah, or something like a status. So nothing really too complex. I can also show you a standard resource object that's working for the food delivery order. So for example, here we have like a standard delivery food delivery order with a pizza, a salad, with a price, a delivery address, and a coupon code and everything. The code for that admission controller does look like this. So we basically have a Python code. That Python code tries to validate the resources. So for example, it checks the delivery address. No, it must be in that format, or it tries to, it tries to check for the price. If the price is, for example, below 0, invalid price on the item and everything. So we do like a little bit of validation here. But there are also built-in bugs for that admission controller. For example, we have like a where do I start? We have, for example, bug over. Now, where is it? The one I tried to. Oh. Yeah, there are some built in, but I try to find the specific one. Yeah, but I show you later then, I think. Okay, there are some bugs built in. For example, there is, for example, not an upper bounds check on the discount. So for example, what we can do is we can set the discount larger than the price on the coupon code. And what then happens is that we get a negative price. So we can like bypass the price tag standardly. Let me shortly search that one. So, okay, yeah. What I want to also show you is the in zip code thing. You can see here in line 25, that one. What happens here is if I cast zip code to an int, and what happens if it's not castable is the admission controller just crashes. And then it depends on the failure policy whether the admission controller really crashes or it doesn't crash, right? Okay, so let's, I don't know why it's just, let's wait some seconds whether it comes up. Otherwise, I'll change the adapter. Okay, there it is again. Okay, so let's run that one in action. So what we can do is we can, or the first thing we do is we need the schemas from Kubernetes. So we need, the fuzzer needs to know how the custom resource definition is structured. So what we can do is we have like a get schemas mode for our kubefuzz. Oops. Pop, pop, pop. So, okay, we have a get schemas mode here. And what we need to give them is an endpoint. So we start a Kubernetes proxy, which basically proxies the Kubernetes API to my local host system. And now what I can do is I do the get schema thing, but I need to add this one. So now the fuzzer downloads all of the schemas. That can take some time. So you see, those are all like valid Kubernetes objects we can deploy into Kubernetes, and it now downloads every valid object from the Kubernetes API that's available. Takes around about a minute. Yeah, there are many standard objects in there. So it's a standard cluster, and I only installed Kyverno and my own like admission on my own demo. So added like 10 resources maybe. Yeah. Okay. Should be done in around a second. Okay, here we go. So what happened now is that we have now our schemas. So for example, our food delivery order JSON. We have, we pulled that schema out of Kubernetes, and now the fuzzer knows, okay, how does an object of the type food delivery order looks like? So now we have basically, we have the schema, so our fuzzer knows how that object looks like. And then we need to write a constraint. Let me copy the constraint we used. A constraint for the fuzzer is, in our case, that we can limit the fuzzer on the input it generates. So what we do here is basically the fuzzer, we can adjust the fuzzer to the input generation so that it doesn't generate like fully random inputs, because, for example, for an array, the fuzzer can generate an array in the length of billion, but we don't want to do that, right? For example, we restrict it here to 4 elements max on the items elements, for example. And we, for example, said that a spec for the Kubernetes manifest is required. So we can adjust our input generation a little bit. And what we do now is we can start the fuzz mode, which is dead mode. And we give the fuzzer, oh, wait, I need to create the fuzzer first. So, and what we do now is we can start a fuzzer. Basically, what we're doing here is we use the fuzz mode. The fuzzer is where the output of our fuzzer is stored in. Then we have the schemas. So that the fuzzer needs to know, right, how the input looks, and then we have the constraint, and all of those goes into the fuzzer. The -e is that after the fuzzer generates 250 errors from the Kubernetes API, it stops, because otherwise it would run for forever. It also runs in a dry run mode. So now it prepared everything, and if I now press enter, we see a little nice UI. Oh, and we are already done fuzzing. That was very, very quick. Let us do that again. Maybe do like 2,500. Oh, yeah. We need that one. Okay. We see a nice little UI. Hey, why do you stop? Oh, yeah, okay, I see the error. Yeah, the main problem here now is that we generated too much of an input for Kubernetes to handle it. But I hope that, let me see. Oh no, I know what happened. Our admission controller is in the wrong has the wrong failure mode. Because in order to get the fuzzer working, we need the failure mode fail. So and now it should be working. Okay, come on. Where is it? There it is. Let's do it again. Yeah, now you also see pop up some errors. The main issue here was that if the admission controller doesn't fail, it will never send any response to the fuzzer. So we need the mode failure. And you can see here how many manifests we generate per second. It's around 160 manifests per second. And we throw all of those against the Kubernetes API. And the fuzzer now tries to, or based on the feedback the fuzzer gets from the Kubernetes API, you can see that with the coverage hits, those are like different messages it gets from the Kubernetes API. So for example, one message might be something isn't allowed or something, oh, again. Yeah. I don't know why this happens, but it's up again, okay. So you can see that here on the coverage hits. So basically each coverage is a different message from the Kubernetes API or a different error message from the Kubernetes API. So now we can wait until the 2,500 errors are done, or we just stopped it. Okay, and then we have the fuzz tier here. And what we see here is we have accepted and errored manifests. So for example, I can look at one accepted manifest, and that is an accepted manifest. So you can see it's like truly random input it generated. So for example, we can order an item named, whatever that means, or an item named GC that isn't a valid like order. So at least I don't know food that's pronounced like that, or that name goes by that. And the price is also like quite high, but it is a valid manifest. So we can deploy that one into Kubernetes. So what I can do apply -f. You see, and now the manifest is created. So and if I do food delivery orders, you see that this manifest is created. And what I can do now is, I mean, there are some bugs in there, and normally the fuzzer, if we run the fuzzer long enough, it also finds these bugs. But I want to show you now manually, because like we only fuzzed for 1 minute. And we cannot expand the fuzzer, or cannot expect to find the fuzzer that quick. All of those issues. So good. So I have here like a standard. Let me show you like that. A standard resource. Then I have a faulty resource, and I have a crash resource. This is what the normal resources look like. I mean, I already showed you that one. Then I have a faulty resource. For example, here's the price is -1. That should not be working, right? And then I have a crash resource. And in the crash resource, I abuse the incast in the zip code. So what we do now is I can apply all of those things. So for example, the standard resource, it's deployed, right? If I try to deploy the faulty resource, what you see is I get an error message that basically says, okay, invalid price on the item. Okay, but now if we, for example, look at the crash resource and the faulty resource as well, you may notice that on the crash resource, the price is still the same. So the only thing changed here is the name. It's now named crash, and the delivery address, where the zip code is set to something that's not incastable. Okay, so deploy that one. Okay. Now you can see that the admission controller has a feedback where it says, okay, internal error occurred, failed calling the webhook. So what happened is, we can have a look at the logs. Oh wait, it's in another namespace. No, how do you? That's your name. What we can see here is that somehow it, tried to incast our value, but it crashed. And now I got this error here. So what I can do with this error is, as I said you previously, most vendors don't run their admission controllers in production on failure mode, because now you can see I cannot deploy anything with that wrong zip code, right? But what if I want to deploy it? What normally is the case is that your admission controller not runs in failure mode, but in ignore mode. So we can simulate that one as well, configure the admission controller, and apply our crash resource. And here you can see the resource got created. You can see on the left, the admission controller still crashes, right? It throws the exact same error. But due to the failure policy of Kubernetes, now our manifest got deployed. And what we can then see here is that our manifest is deployed. And those are the types of bugs we try to find in the future. So there is a page called Operator Hub. Who knows Operator Hub? Okay, Operator Hub basically is a website where you can find all of those Kubernetes operators. So for example, AWS. As I said to you, there are different distributions, and every Kubernetes distro has its own, like, let's say, specialities. And in every AWS cluster, you can install, for example, an operator that manages, what do we have here? For the Amazon API gateway. That's a known operator that manages resources inside of Kubernetes for AWS. And what we want to do is we want to test all of those operators, all of those admission controllers that we have here, because normally they come bundled. So for every operator, every custom resource, you have your admission controller, and we want to test those on security. So we want to integrate, or what we will probably do is we build a huge cluster and install all of those operators in there, and then try to fuzz all of those resources and see if the security of those operators and admission controllers are good. So that's what we try to do in the future. Okay. And whoops, where is it here? Yeah, that's from my talk. If you have any questions, don't hesitate to contact me or anything, or some other Kubernetes security topics. I'm willing to discuss with you. Hopefully you liked it. Hopefully it wasn't too complex for the short time frame, because I think it was much of information. But thank you very much for listening.